Welcome back to the third part on bit manipulation. So let's do some more black magic with the bit manipulation today. And what we are going to see primarily is the shift operation. So we'll look at the shift operations and we'll see how to set and clear bits. So this is something that the bit operations are supposed to be used for, that you have again the 32-bit register, and within that some bits need to be extracted out, some bit needs to be set for whatever reason, reasons we'll talk about as we master these tricks. So you might want to clear certain bits, you might want to set certain bits, and for that you can imagine that we need some sort of bit manipulation. Okay, so what bit manipulations do we use? Well, the usual trick is use one somehow to move it. Okay, I need to use, uh, I'll put myself here. Okay, so here's the thing, and this is a very, very simple trick. There's just like a way to look at things, and this is how you look at things. Okay, so assuming again that we have 4 bytes, and why 4 bytes? Well, an int. If it was a character, well, then we only have 8 bits to play with. If it was a short, we only have 2 bytes to play with. If it was a long, we have 64 bits to play with, or we have 8 bytes. What does it mean, play with? It simply means the room for the movement, the shifting operation is limited by the size of the data type of the variable on which we are going to do shifting. We have been doing shifting on an int type, so it has 4 bytes, and that's why I'm using 32 bits, talking about 32 bits. If I were to shift something by 32, well, then all of that data is thrown out of the register. We'll take a look at that. But okay, let's talk about the usual, most common thing done as part of bit manipulation, which is set and clear bits. This is where we are headed. Now, let's say we wanted to clear 15th and 14th bits. We want to clear those. Well, so the first thing is we want to isolate those. We want to very specifically target those. And how can we target? Well, let's take another register with just 1 in it. Then first, let's push it to the 15th position. Take another register with 1 in it, push it by 14th position. Then can you think of an operation that can give us 1, 1 in the 14th and 15th position? Well, if we OR both of these, we'll get something like so. All zeros here, all zeros here. Great. So ORing operation is used to kind of enable bits. There was a 0 here, there was 0 here. And now we got the combination came out like this. Now we have everywhere zeros, and only these 2 bits are 1, 1, and they are exactly at the position of the, let's call it, victim. So we wanted to target the victim, and the 14th and the 15th bit within that victim int, let's say. And now we have all zeros here, all zeros, just the 14th and the 15th bit set. So now if we were to do some operation between these two, well, we are going to have an effect on 15th and 14th. Now the question is, okay, do you want to set these bits? If you want to set these bits, simply OR, because ORing will result in the bit being set if it was not set. If it was a 0, an OR with 1 leads to 1. An OR with uh, a 1 and a 1 also leads to 1. So whether or not they are set, if both of those bits need to be a 1, we just want to OR it with 1, 1 at that bit positions. So these bits will get set. Now what about clearing those bits, 14th and 15th? How do you go about doing that? Well, for clearing, how about we had ones everywhere else except here? So 14th and 15th was 0, everything else was 1. And if we ANDed it with the original, what will happen is everywhere there was a 1, well, that will continue to stay a 1 because 1 ANDed with 1 is a 1, 1 ANDed with 0 is a 0. So because everything here is a 1, the ANDing will result in the same bit that was originally here. So effectively, we are not touching the bits that are already present. But the interesting thing is, these two bits here, 14th and 15th, will be 0. And so when we AND them with the original can be 1 and 1 or 1 and 0, or whatever combination. But what it will ensure is when we are ANDing them with a 0, the answer is a 0. So remember this, whatever you OR with 1, the answer will be 1. Whatever you AND with a 0, the answer will be 0. And this is fundamentally at the base of set and clear bits. And how do you reach out to the target bits? Well, the answer to that is shift operation. Now, one other thing, if you, which is here. So I simply mentioned that how about we turn all of these into 1 and 0 here and ones everywhere else. How do we go about doing it? Well, we initially created this 1, 1 and everything else as 0. If we simply perform the NOT or inversion operation on that register, all the bits will flip. And as a result, we get the exact thing that we wanted, which is ones, 0, 0, ones. So this is something to remember, right? Setting and clearing the bits will involve OR to set and to clear. And AND with what? So OR with 1 and AND with a 0. And then to target the bits, we need to use the shift operation. And the shift operation helps us create something called mask. The standard term across the open source community is mask. So you create a bit mask, so to speak, to isolate. So now, let's play around and take a look at these a little bit. And the only way to deal with such kind of things is by practice. But hopefully the shift operation we looked at yesterday, now combined with the AND, OR, and NOT operation, gives us the ability to isolate. Okay, let's then open up the main.c. Okay, a lot of stuff here. What I'm going to do, and I'm going to keep the example simple right now, and then we'll kind of peel the layer. So right shift is not something we'll use as much. Rather, it's the left shift because we typically have we want to create the mask, so to speak, by shifting 1. And again, shifting 1 is not the only trick. You can shift 1, you can shift 3, you can shift 7, you can shift F if you want to isolate 1, 2, 3, and 4 bits. And that can go on. Okay, so let me then, okay, first off, let me click here. And yes. So let me call this victim. and we'll use the hex notation to fill the value. So let's fill a value of A, B, C, D, E, F, and I don't know, 2, 3. Right? So it is exactly 4 bytes. You know, these are representing nibbles. A nibble is a 4-bit. So 2, 3 is 1 byte, the lowermost byte, the second lowermost byte, the second highest byte, and the highermost or the most significant byte. Right? All right. So we have this. Let's go ahead and then do like a printf of, and I'll do like a %x of victim, and let me do /n, then go ahead and let me also actually put a 0x here just so that things are printed nicely. Victim. Okay, let's save this. Let me compile this. Let me run this once. Well, great. So A, B, C, D, E, F, 2, 3. So no problem. And let me actually increase the font size so that you can see it even more clearly. Okay, let's go to our file and start to now make changes. Let's say I suggest or I want to isolate E and F. How do I do that? So again, based on our initial understanding of what I mentioned about creating, let's say, masked victim, right? 0x%x, and then we have /n. So now we have the victim, and what I'm interested in doing is I'm interested because I'm wanting to isolate. I'm wanting to do an ANDing. Why ANDing? If I AND with 1, okay, here's an explanation. So victim is here. And let me divide it into 4 parts. So 2, 3 is right here. E, F is right here. C, D is right here. And A, B is right here. What I now want to do is I want to isolate this. So I know that it is starting from the bit position 8 because 0 through 7 is the first byte, and 8 through 15 is the second byte, or the second, what do you say, the, well, EF from the left, right? So what I'm now interested in doing is somehow I want to isolate this and discard everything else. So I first have to create a mask for this, and mask is how many bits here? Well, I want to isolate 8 bits. So much like in the previous, small example that we took, we wanted 15th and 14th, so 1, 1, and this mask was 2-bit mask. So here I want to create 8-bit mask. How do I do that? Well, what I know is whatever the mask is, if I perform an AND operation, then I have the ability to either make this a 0 or make everything else 0. And why do I say that? Well, we talked about setting 14th and 15th to 0 by ANDing them with 0. So what I then propose, and we said that everything else, by the way, on the side will stay as is because they were ANDed by 1, ANDed with 1. Based on the same logic, I want to propose the following. What if I ANDed these 15 to 8 bits with 1 and everything else with 0? Then I effectively discard everything on the right and the left of 8 to 15 and only get EF. You follow the logic? So I'm saying if we AND something with 1, the value stays whatever it was. If we AND something with a 0, the value becomes 0. Similarly, if we OR anything with 1, the answer becomes 1. If we OR anything with a 0, it stays what it is. So I'm wanting to use that trick of ANDing everything else with 0 except the bits I'm interested in. And if I AND them with all ones, then I'll extract those out. The question now is, how do I and then with 1. What I do know is I can shift 1 to these different places, 8, 9, 10, and then I can essentially continuously extract bit by bit, and that's a way to do it. So let's go ahead and try that. It's a little expensive. What I can do is I can isolate and 8th position with 1, extract that bit, or it with a 0 register, and so that bit gets set. Then I can AND this register again, but this time with 1 shifted by 9, so the 9th bit is isolated and I get back the bit value of 9, and then I OR it with this modified register, and so this bit gets set. Again, recall, ORing sets a bit if it is 1 and leaves it as is if it is not. That is one trick. So what I'm going to do here is go the complex way first, complex or advanced way first, which is, again, uh, which is, I'm wanting to target 8 to 15. So I know that these are 8 bits. And can I have a mask that spans 8 bits and is all ones? Well, I can hand code it. So 1111, 1111. Hey, this looks like F and F. So if I take hex FF and shift it to the left by 8 bits in a 32-bit register that is FF at the bottom, if I move it by 8, all these bits will get shifted to here, and this will be zeros. And if I manage to do that well, then I can just simply add and these, and the isolation will happen. Let's quickly take a look at that. And I'm going to do this as a compound statement, or rather, let me not do it as a compound statement. Let me do it like so. I'm saying it's a mask, and then the mask is FF, but FF shifted to the left by 8. And then let's go ahead and print the mask. And I'm going to use the same trick, which is %x/n quotes and then the mask. And let me actually just comment this line out, because let's just first print the victim and the mask, and then let's see what happens. So this is commented now. Okay, there needs to be a semicolon here. Nice. So I'm going to right quit this, compile this code, and run it. Well, do you see this? So we started off with the mask as hex FF and shifted it to the left by 8. What that did was started off with an FF here, and as you move every bit to the left by 8, this F eventually came here, and this F eventually came here, which translate to 1111, 1111. The 8 bits from position 8 to position 15 was set to all ones. Perfect. So now then what I propose we do is we want to isolate. So I'm going to edit, and here I'm going to use the ANDing. So the AND operation. Let me compile this. Let me run this. Well, do you see EF getting isolated? So the masked victim now, exactly this got removed. This is set to 0. This is set to 0. And in fact, this is set to 0, hence we don't see anything here on the left of E. But you see this is now EF00. So we deleted this and retained this. So that's the magic of creating masks. Now, okay, I jumped the gun here and talked about creating masks in the sense that you need to know, how many values that you're wanting to, or how many bits you want to isolate, and then what do you want to do with that bits. Now, here's the thing. Instead of, remember, our mask is FF00. I mean, this line here, once it's computed, the mask here is FF00. What happens if I OR? Oh God. Okay. What happens instead of performing the AND operation here, I perform the OR operation? Can you reason about that? So we have the victim, and we had this, 8 to 15 bit, which was EF. And then now we are saying, hey, we have all these ones here, which is effectively FF. And what we are now doing is, instead of ANDing, we are wanting to do ORing. And remember, when you OR with ones, the zeros will get converted to 1. The bits get set. So then what we get, and hold the answer with you, what we will get is we'll get FF00. So what happened here? I said FF00, but what happened? Well, it's an OR operation. So this was the victim, and we targeted bit 8 through 15, and they were FF. So notice in the ORing operation, the bit that was a 0 here got set to 1. So the E here, where was that? So the E here, so this is E and this is F. So this bit got set, and as a result, this got converted to F. So we see an FF here, but everything here was 0, everything here was 0. ORing anything with a 0 retains the content as is, so that came down, which is 2, 3. And this side came down as A, B, C, D. So ORing with a 0 retains the value as is, and ORing with a 1 sets the 0 bits. Similarly, ANDing with all ones retain the value, and ANDing with zeros resets the bits. Now let's try that. So how about, instead of, so here the mask was FF all zeros. Now what I'm saying is, we should create something which is like so. How do we do that? And the trick I had suggested was that we simply invert the mask, and all zeros will convert to ones and all ones will convert to zeros. So how do we do that? Well, what we can simply do is, on the next line, simply have this mask equals to inverted mask. So take the 0000 FF00 and convert it into FF00FF. Let's see what happens here. Actually, let me actually put this here, and let me how do I copy this? I think it's yank. Let's see, paste. Yes. So let me put this like so here. First, let's just go ahead and print that. You see this? The inverted mask, exactly the inverted version of this. FF00FF. And now what I propose we do is go back, and instead of ANDing, instead of ORing, we AND it. Now you can guess the output. So, well, let's see actually. You see that the second byte, EF, because we ANDed it with zeros, it was set to 0. It was cleared. So this is how you go about then, setting and clearing bits. Now we talked about group of bits, and as you can imagine, it's a function of your mask. If you want to target multiple bits, well, create a mask that targets multiple bits. If you're wanting to target one bit, create a mask that is one shifted by n places. Now you can sometimes, okay, let's take a look at one more complicated. Let's say I wanted to clear not only the, okay, let's draw a diagram. So not only do I want to clear the second, but well, okay, bad diagram. Well, not only do I want to clear the second byte, but I also want to clear the MSB, the most significant byte. MSB is also most significant bit, but because we're talking about bytes here, MSB can also be understood to be most significant byte. All right, so we are then trying to isolate or clear this out, clear this out. How do we do that? Well, here's an interesting thing. Many ways to do this. One can be we create a master mask, right? So one way to do that would be, hey, okay, let's do this. Let's take our, actually, let me do so here, here. So I take the original mask and I say, hey, let's do this. Let's take the original mask and OR it with a shifted version of that mask by 8. What does this mean? Let's see. In fact, let's also correct ourselves. So initially, our mask was FF, 0, 0 here, all zeros here. What we are saying is, let's take this and let's OR it with a shifted version of itself. And shifted by how many? Shifted by, okay, let me draw this correctly. So let's take the mask itself and shift it to the left by 8. So what happens? This comes here. This comes here. This comes here. And zeros are padded here. Well, this is incorrect, right? We actually wanted this F here. So instead of moving it by 8, what if we moved it by 16? Then this would go here because it is shifted by, this entire thing will get shifted here, right? It will come here. So we have 0, 0, FF here and all zeros here. But then how about we OR both of them? Then we get FF 0, 0, 0, 0, FF. And remember, ORing with all ones essentially sets the bits. So we are using the trick of ORing and ANDing to create a better mask by using an initial mask. And that's what happens. So instead then of us moving this by 8, let's move it by 16. And then let me go ahead and print let's see, mask ORed with mask moved by 16. And we are saying, hey, modify the original mask. Right? So this is essentially creating new mask using the old mask value. And what was the old mask value? Well, this one. And then this point on, at the whatever follows, the mask value should be FF00, FF00. And then as we invert that, we will make it 00, FF00, FF. And then we are saying, hey, AND it with the victim. And so that way the upper byte here and the second lowest byte are killed or are zeroed out. Let's look at that. Let me now compile this. Let me run this. Well, do you see? 2, 3 remains, EF is gone, CD remains, and AB is gone. And because it's zeros, it's not showing it here. Now, one could argue, hey, aren't there other ways to do this? Why did we invert the mask here? Could we not just start with FF as our mask, then shift it to the right by 16, right? So which then gives us something like FF, then move it by 16, so gives us this. This is essentially what we started with. What if we started with FF00 as a mask and then simply shifted by 8? Wouldn't we get FF00, and OR it with itself, FF00? And this is the same mask that we ended up creating with this inversion operation. So we could have avoided the inversion had we chosen a starting, instead of this, had we chosen FF00. And the answer is, yeah, correct. We could have done that. So there is no one way to do bit isolation. There are many ways, and all of them are correct as long as your final output or final intended um, operation is complete. Now one could argue about, hey, which one is more optimized? Well, we'll talk about all of those in the next lecture. But as part of this one, then what I wanted to show you was how shifting is involved, along with something called creating masks. And then using the masks, we can use the AND or an inversion operation in varying form to create exactly the bit pattern in the mask that we want, and we have to AND or OR with the victim to get the desired result. In the next one, we'll all kind of dive a little more and explore the usual other things that is done in the open source in terms of shifting the bits and why they are used. Let's talk about that in the next lecture. All right, so I'll see you there. And if you enjoyed this one, do leave a like and a comment. It helps the YouTube algorithm push this thing forward. And if there are friends and colleagues that can use this information, do pass them along, pass the video along to them. All right, cool. So I'll catch you in the next one.